And so not all rings will have p orbital, not all atoms. And so hybridization, which we will begin today. Got to be able to know hybridization, what atoms have what orbitals, which atoms will have p orbitals under what hybridization. Got a minute left. I'll take up your questionnaire sheet. Which textbook you're using? My textbook from when I took undergraduate organic here, kind of falling apart a little bit. We're going to have some quizzes. Quiz 1, January 12th. Oh, I had 10 on that one. 9.
I'm going to be wearing my rose tattoo. Don't read it.
A lot of 9s.
Like, please don't.
$67, brand new. Also, there is a guide to preparing for the American Chemical Society exam in the bookstore. Most students buy this in Organic 2. But why not buy it now? It has chapters on topics I'm covering now. So if you're looking for extra problems and getting a head start on preparing for this, this is available in the bookstore. Preparing for your ACS exam, you probably get it on Amazon as well. Okay, guys, good morning. Let's get started. If you please pass in your questionnaire sheet to the sides. Pass them all to the sides, please. Sides.
Thank you. Thanks, sir.
This is all of them?
I really hope he doesn't read.
You will.
Okay, give me a light on this. Functional groups. I think we maybe were running out of time when we look into this. Nitrile, sulfonamide. Sulfonamide, I want you to know, sulfonamide group is in lots of drugs actually, a lot of anti-diabetics, antibacterials, some anti-cancer compounds. There's some examples of identifying functional groups. There's a couple more listed over here. When the alcohol group or the hydroxyl group is on a benzene ring, it's called a phenol. It's a special type of alcohol. We call it a phenol. It's got the OL ending in alcohol, OL ending indicating phenol. When the amine, there's an amine, tertiary amine, it's got the bottom of 3 carbons. But it's also an aniline. Well, there's no aniline in these structures here. When the amine is bonded to a benzene ring, it's called an aniline. Some people may say aniline, like amine, ene ending, but nobody really says that. Aniline. So we call them those special names. So please know those 2 others. Any questions about that page? No? Remember, the subtitle of this course is How to Ask Questions. Very important. Why do I think it's very important? Well, students who typically ask more questions do better. It shows that you have prepared in a more particular and valuable way that your professor is recommending, because your professor has seen many students do well and not well. That's a recommendation. If you're looking for recommendations on how to do well. Okay, hybridization, warm up. Got a handout today. I realize why I like to email on more, because These had to be stapled individually, one by one, because the copier was out of staples. Hopefully they were all stapled nicely. This is a physical properties handout. We may be getting to this. Of course, solubility lab this week in lab. Daily questions, how are we doing on some of those? Any questions about the daily questions? No? Let's look at hybridization. Let's see where we're at on the green sheet. That's our outline. Functional groups. Gave you a little bit of advice there under number 3. Roman numeral 3. Formula C7H6O2. How many DUS does that formula contain? 5, yes. Okay, 5. It's got 5 DUS and 7 carbons. Can it have a benzene ring? Yes, benzene ring is 6 carbons and 4 DUS. So benzene would fit into that formula. Okay, you draw a benzene ring, you already got 6 carbons up there. You only need 1 more carbon on your benzene ring. The functional groups are ways to quickly get structures together. We were doing some very systematically. Okay? C7H6O2. Okay, benzene ring. Already that's C6H6, but we're going to put something else there. That's 4 DUS. The formula shows 5 DUS, right? We also have 2 oxygens. You don't need functional groups that contain 2 oxygens. Yes, carboxylic acid. Okay, we can put that up here, but that's only C6. O2, 6 H's. No, that's 7. 6, 7, C7, H5, 6, O2. There you go. You see, I just put up 2 functional groups that I know, getting to the formula. Understanding 4 DUS. So you don't have to do it so systematically, 1 carbon at a time, if you know your building blocks. Use those building blocks to put structures together quickly. Okay? There's a couple on the DQ page. Hybridization, Roman numeral 4. Let's look at methane. Here we go. I believe we drew methane before, right? CH4. 1 carbon alkane. You got the nomenclature handout in video. 1 carbon methane, 2 carbon ethane, 3 carbon. Okay, so that's the beginning of nomenclature. 1 carbon alkane. Alkane functional group is what? A saturated hydrocarbon. Right? No DUS. When we first drew it out, we probably just drew it like this. These bond angles we did not consider bond angles. As drawn, this looks like what in 9th grade geometry? 90 degrees?
Linear.
Linear?
Yeah, because it's flat, but it's supposed to be tetrahedral.
Okay, it's supposed to be tetrahedral, so we did not draw it actually correctly. Let's look more precisely at bond angles, geometry, hybridization. Okay? Yes, we know it's actually tetrahedral. Okay, let's approach this a little systematically. Ground state carbon. When carbon bonds, it bonds in a hybridized state. Whenever you learn ground state configuration in Gen Chem, that's just like the very, very beginning. I actually don't know why you really learn it, other than that's just the starting point, because everything carbon bonds hybridized, different from ground state. Hybridized meaning just a fancy word for mixed orbitals. But we do have ground state, right? And we have the, and I'll draw this once, and from then on out, I'll just refer to it. We've already drawn it last time. We have the 2s, right? And then we've got the 2p. I'll make a little space here, right? We got off-bound principle, Pauli exclusion principle, all that. Fill these in. 1, 2, 3, 4. These are arrows denoting the electrons. Ground state, some type of energy, yeah. Okay, carbon doesn't bond this way. We're going to mix these. Okay, very importantly, how many electron regions around this carbon? 4. Each bond is an electron region. 4 regions is best spread out how? Tetrahedral. 3-dimensional. Okay? Bond angles. This is only 90 degrees. Can we get greater than 90 degrees? Can we spread these out more? This is about 10 degrees, right? The more we can spread these out, that's 90. Can we spread that more?
Yes.
We can, yeah, how do we go to 109.5? Tetrahedral gets us there. 3D. Okay? If I brought in 4 balloons and tied them all together at the little tie part, guess how those 4 balloons would spread out? They would spread out in a tetrahedral manner. That's nature. They're going, okay? It's the energy being just spread out as much as possible, essentially. Okay. 4 regions, you need 4 hybridized orbitals. You only got 4 here. Because we need 4 hybrid orbitals, we've got to mix all 4 of those. Because if you mix 4, you get 4, which is what we want. If you only mix 3, you're only going to get 3, but we want 4. So we've got to mix 4 to get 4. So we're going to mix them all, okay? Boom. And we're going to come out with, hold on, before we go on. We know something about these bonds. This is 4 equivalent bonds. We know that from experimental evidence. We can probe the molecule and study it. 4 equivalent bonds. First off, how do you get 4 equivalent bonds with these 4 orbitals? First off, that looks like a lone pair. It's 2 electrons in an orbital. I don't see a lone pair here. And then how am I going to get 4 equivalent bonds using 3p orbitals? You're not. We've got to hybridize these first. All 4 of these go into the blender, okay, like ice cream. 3 scoops of chocolate, 1 scoop of vanilla. Put it into the blender. What do we pull out? 4 scoops of somewhere in between. Okay? They're supposed to be the same level there. 4 identical orbitals now. What do we want to call these? Well, not too fancy. They were created by combining an S and 3 Ps. So we call them sp3. It's 4 sp3 orbitals. 4 of them. We blended these 4 up and scooped out 4 blended ones. This is really a lot of math to understand the fundamentals of this. Mathematical combination of atomic orbitals, that type of thing. 4 equivalent orbitals. Now we can put our electrons in 1, 2, off ball, etc. 1, 2, 3, 4. Now we're set up to make 4 equivalent bonds using mixed orbitals. Again, a lot of math to getting to those mixed orbitals. Physics and math and all that good stuff. Now we can come in with maybe a hydrogen and it's 1 electron, hydrogen 1 electron, hydrogen 1 electron, hydrogen 1 electron, and make 4 equivalent bonds, sort of like we did last time. And this is 4 sp3 hybrid. Okay, we can call these hybrid orbitals. What's the energy of these hybrid orbitals? And what does this orbital look like? We'll try to draw or approximate a little bit. What's the energy? The energy falls between this. It's just like I asked you 3 chocolates and a vanilla. Well, what's the resulting flavor? Somewhere in between chocolate and vanilla. But if 3 chocolates went in and only 1 vanilla, the mix is going to be more like chocolate. Or if you want to talk about colors, 3 reds and a white, mixed red and white, what do you get, pink? But 3 reds and a white, it's going to be sort of a hot pink, a dark pink, because there was 3 reds. 3 gallons of reds, 1 gallon of white, okay? So in the end, the hybrids are going to look kind of closer to these because 3 of those went in. So in terms of energy, relative, you might say it's closer in energy to these. As we go along and we get other hybrids, we'll compare. Okay, what do they kind of look like? That can be tough to draw from scratch. We're mixing these. I'm not going to mix an S and 3 Ps. Let's just mix an S with 1 P. Okay? Now the S has a phase. The P has phases opposite like this, lobes. Again, a lot of math. But in the end, this phase constructively interacts with the positive of the S, 2 same phase. And so on this side of the nucleus here, you've got some reinforcement, and you get sort of like that. But over here, where this is all negative, and that's positive of the S, this is destructive overlap. And so it kind of cancels each other out. This is like 2 waves building to make a bigger wave, but over here, 2 waves coming together and canceling it out. Can that happen? Yeah, sound waves too. You can have pockets where there's no sound because the sound waves cancel. That's what happens over here. So over here, it doesn't completely cancel, but you get something sort of like this. And this would be sort of showing an SP, where we combine an S and a P. I'm not going to try to put 3 P orbitals up here. It gets too convoluted, I can't draw that. This would be the back lobe. Typically, the back lobe is not usually drawn when you draw these out around an atom. It gets too cumbersome. Back lobe is there. We'll mention it later on during test 3 when we do backside attack. Okay. So, I'm not going to try to draw an sp3. We'll say more about relative appearance of those. We've got 4 of these. How are they spread out? I'm going to erase this here. Tetrahedral, not 90 degrees, but 109.5, greater than 9. How do you draw tetrahedral? 2 in the plane of the board, flat on the board. 1 forward, and 1 back. Okay, get some practice at drawing this. That's my first attempt at a tetrahedron. I lost my
Erasers right there.
no, I'm looking for toolbox. Okay, so the plane, 1 forward, 1 back. But these are the orbitals here. To me, it's easier to draw a line first, then draw the orbitals. What does this look like? We have some type of orbital. Okay? Now there's a back lobe back here. But you see why it's not drawn? Because then you got something else drawn over here. It's going to be on top of it. So let's don't draw the back lobe. Nucleus being right in the middle. So each one of these are orbitals, right? And that's an sp3 orbital, sp3, sp3, sp3. 4 of them all around in a tetrahedral manner. This is 109.5. Between any of the 2 bonds. I'm not going to label all of them. Okay, then with methane, what is this orbital interacting with?
Another methane?
No, this orbital is interacting with a hydrogen. This is the carbon orbital, then we have a hydrogen. We're going to make methane here. What orbital is the hydrogen using? S, yes, 1s. Okay, this is actually the second shell. Okay. 1s, what's S look like? Just spherical, right? So this is the 1s of the hydrogen. And then what's going on here when these two orbitals interact? First off, how many electrons are here? 2, right? I mean, we're looking at one of these, made a bond. 1 electron from hydrogen, 1 electron from carbon, interacting in a magical way, book that thick, to make, what type of bond did we just make? Using an sp3 and an S. What type of bond is this?
Sigma.
Sigma bond, yes. Sigma bond, head-to-head overlap of orbitals. Head-to-head overlap. And so you got this all the way around. I'm not going to repeat it, but yeah, you see 4 identical, right? 2 electrons, 2 electrons, boom. Here we go. Sigma bond head-to-head using a hybrid and in the 1s. The H orbital is not hybridized. I mean, it's just one orbital. It's just the original S. Questions about methane? 109.5. 4 sigma bonds, head-to-head overlap. We'll say more about this. I'll try to save my original ground state. One important thing about sigma bonds is they can rotate. I apologize, guys. I took my toolbox off my cart, and I don't have any backups. I cleaned out everything. We'll review this with some demo on Wednesday. And also some nice colored pictures I can show you online, which will be a lot better. Not too much better, that's a pretty good drawing there. Colored pictures, and there should be some in your textbook. Okay, next, ethene. Slang name being ethylene. 2-carbon alkene. You got to have 2 carbons to have an alkene, right? This is going to illustrate sp2. So, this illustrated sp3 hybridization, 109.5 geometry. Ethene. I need to erase that over there. Let's draw it over here. Here's ethene. Each one of these carbons illustrates sp2 hybridization. How many electron regions around this carbon? And the answer is the same for this. 3. Single bond, single bond. Double bond is 1 electron region. So 3 electron regions. Okay? If I tie 3 balloons together, how would they spread out? Yeah, they would spread out in trigonoplanar arrangement. Okay? Your hybrids set your geometry. Number of hybrids set geometry. We need 3 hybrids in this case. We get 3 hybrids by combining an S, not all 3 P's, but an S and just 2 P's. All right? So I'm just going to combine this. Now I'm going to hybridize. And I'm going to get, if I put 3 in the blender, how many do I get out?
3.
I get 3 hybrids. What do you want to call these?
SP2s.
Yeah, it's real sophisticated. It just, what went in to make them?
1S.
S and 2 Ps. 3 sp2 hybrid orbitals. What do we not put in the blender that's left over? Yes, it's there. Okay? It's there. Now we put our electrons in. 1, 2, 3. Now, from off-ball principle, those things, you might put the next one here. But actually, it's going to sit here. And we make 4 bonds here. But they're not going to be 4 equivalent bonds. We're going to make 3 sigma bonds. When you use your hybrid orbitals, you're always making sigma bonds. Head-to-head overlap sigma bonds. But then we're going to make a bond using a p orbital. And when you use p orbitals, we're going to be making pi bonds. Okay. Now let's see if we can draw this here. Carbon. 3 hybrid orbitals, how they spread out? Trigonal planar. So I can have 1. Now a lot of times my orbital may just look like, is that a p orbital? I mean, depends on how, you have to draw them both, but no, it's not a p orbital. I'm drawing the 3 hybrids. Boom. Let's see. Let's start with lines. That may make it easier. Boom. What's trigonal planar? Something like, those 3 lines look trigonal planar?
Yep.
All on the plane of the board, nothing forward, back, all on the plane of the board. What's the bond angle with trigonal planar?
120.
Yeah, that's 120, right? Or can we go, okay. But this is really not lines, it's orbitals. It's these 3 hybrid orbitals in this arrangement. And that is 120 degrees all the way around. Boom, boom, for a total of 360. So trigonal planar. So what is this carbon bind to here and here? The H's, right? So that's the H. This is the H. That over there is the same as this, right? It's 1 electron from carbon, 1 electron from H. You've got the 1s orbital, and you've got the sp2 orbital from carbon. These are interacting to make the magical covalent bond. 2 electrons here, right? Boom. And X, 2 electrons. Same thing here. What is this hybrid interacting with? Actually, the other carbon. So here we got a carbon-carbon sigma bond. And it's the same exact thing, trigonal planar. So I'll draw it like that. And lo and behold, 1 electron from this carbon. Instead of just drawing X's, I'm going to draw like this. 1 electron from H, 1 electron from H, 1 electron from carbon. Okay? And I'll draw it like that. 1 electron from this carbon, 1 electron from the other carbon, making that. And then this guy is the same thing as over here. I just won't complete it. Well, maybe we should. It's the same exact hybridization, right? Importantly, though, so there are 3 sigma bonds. What else is on this carbon we haven't drawn yet? P orbital. I'm going to get rid of this. I can draw it there. Now it's the p orbital. It's here. I'm going to draw it a little longer so it looks a little bit elongated compared to the hybrid. This other carbon is the exact same hybridization, etc. It's got a p orbital left over. Now when we draw the p orbital is actually orthogonal or perpendicular to that plane. The trigonal planar, if the trigonal planar is in the plane of the board, the p orbital is actually coming out at you. If you want to draw the p orbital straight up in the board, you have to envision that the three planars are actually like this instead. Okay? Now, it's hard to draw that, especially unless you take a lot of time. That's where it's best to look at some color depictions, and they'll give you more of a 3D view. So, this carbon, one electron in the p orbital, right? Well, the other carbon's also got one electron in its p orbital. And I'll call it a C instead of an arrow, whatever you want to do. But guess what? These two orbitals, one electron, interact. How are they going to interact? Well, trust me, they can interact. But they're not interacting head to head, they're interacting what? Side to side. Okay? I wish I had the old pen. But the old pens, you could bond them together. These won't bond. Head to head, sigma bond, side to side, pi bond. Now it looks like these are far apart. Well, they kind of are in my depiction. In real life, all this is probably a little closer and doable. I've kind of drawn it a little wide. The pi bond is weaker. It is weaker, perhaps because of this distance, and there's not as good overlap. That may be one reason. So what do we have between the two carbons? We have the sigma bond, and what else do we have? We have the pi bond, which is, all the way through here, side to side, all the way through. So how many bonds between the carbons? 2, double bond. And so right here is your double bond, carbon-carbon double bond made up of a sigma and a pi. P orbital interacting. Rest being hybrids. Hybrids set your geometry. They're spread out in a trigonal planar with 120-degree bonding.
Are there electrons on the bottom part? Because I know you just wrote that on the top part of the pot.
Well, it's a p orbital. I mean, the electron density is right both sides of the nucleus.
Okay.
P. Dumbbell shape.
The one on the right would have, in this case, it'd have an arrow on like the bottom right for the P. Yep.
I mean, that's an electron.
Yeah, that's an electron. Then go below that on the bottom one.
Here?
Is that just mirrored? Is that the same thing?
No, that's a p orbital.
Okay. Oh, the whole thing is okay. Correct.
The p orbital, right? Nucleus.
Yeah.
Where's the electron? It's
Yeah.
It's everywhere.
There are two
That's
different
it. That's
ones,
the
my bad.
distribution of the electron. No matter where I drew my arrow, orbital means that's where the electron is. Question?
So where you have the sp2, where you showed the hybridization, did you do 3 and then the one on top because there's 3 regions with 4 valence electrons? Oh. But the one above it, why did you put them on top? Like why did you put it above the rest of it?
How many regions do we need? 3. So you need 3 hybrids. The one was put on top because it's there and we didn't use it. We didn't use this. So I just redrew it over there.
Does that indicate that it's a higher energy? Or just, it just...
Well, let's talk about energy. What type of orbital is this? P's, right? Which is higher in energy, a P or an sp2? Why P?
It's the hybridization from the S.
Because an sp2 has some S character. And S is lower energy, right? So if you start mixing in something with lower energy, which is more chocolatey? Pure chocolate or chocolate with a little vanilla?
Pure.
Pure chocolate is higher in energy in this scenario. Okay? How about shape? Which is longer? A p orbital or an sp2?
P,
Why p?
because it's not mixed with the S.
Because once you start putting s character into the orbitals, this is where I'm not going to draw it, but I can explain it. Well, s is not long. It's short and fat and roundy. Okay? So if I start mixing in this with that, it's going to shorten the more you put this in, the shorter it's going to get. There's in between. And if it's 100% S, well then that's it, 100% P. Hybrids are in between. But in terms of S, what percent S is this? You often state that. What percent S is in here? Yeah, so you just 33% S. What about the sp3s? What percent S was that? 25% S. So which is longer, an sp3 or an sp2?
SP2.
sp3 would be longer. Less S character. Less S character, longer it's going to be. More S character,
Short.
shorter it's going to be. Okay, there with the hybridization. You got to draw. So you need to understand when you look at a structure, you need to understand what type of orbitals are being used to make the bonds there. Difference between sigma bond and pi bond. One big difference with the pi bond is pi bonds cannot rotate. Because if these are pi bonded side to side and you try to rotate this guy like this, okay? So if I rotate this bond, boom, you see how the orbital moves? Okay? Side to side. If you do this, you've broken the bond. That's no longer side to side overlap. Okay? But head to head, again, you can rotate this and they can still stay bonded. I'll demo this on Wednesday. That was important there. Ethene. This is where we're going to put a Y in here. Ethene. So this is our alkyne, 2-carbon alkyne. That would be HC triple bond H. Each carbon is the same. This carbon here, how many regions around it? Electron regions?
2.
2. A single bond region, triple bond region. 2 regions are best spread out how? Linear. If I tie 2 balloons together, they will spread out. Linear. Do you ever tie 2 balloons together and they spread out like L-shaped? Let me know. Nobel Prize. Linear. Okay. How many hybrids do we need? Hybrids set your geometry, so to get
2.
do I? 2. Because if we had 3 hybrids would give you trigonoplanar. If you had 4 hybrids, you would get tetrahedral. Hybrids are like your balloons. We got 2. That's what it's linear. Okay. So we, don't worry about drawing this. You can if you want. I'm not. There's your ground state, right? We need 2. That's not ground state. I should not erase. Ground state looks like this. We want 2. We're going to combine an S and 1 P. We're going to leave 2 P's behind. Okay? And so we get 2 hybrids. You can draw these wherever you want. Those are original. They should be the same energy. Okay? Those are P's. These are called, yes, SPs. We have 2 SP hybrid orbitals because we want a linear geometry. We see a linear geometry. We have 4 electrons. And now we're ready to make how many sigma bonds? 2 sigma bonds and 2 pi bonds. Carbon. Okay. Drawing the hybrids. How's the length of this going to compare to maybe sp3?
Shorter.
50% S. Shorter, more S characters shorter. Functional group handout, last page. Does that trend make sense? Fancy drawings, yeah? More S characters, shorter, more rounded. But up here, I'm not going to try to be so specific. I'm just going to say boom, and that's what, an SP. But a back lobe, I'm not going to draw that because over here, in a linear manner, we got boom. Okay, they should be the same size. SP. What is this orbital interacting with? The H, right? You got 1 electron from carbon, 1 electron from H, magical covalent bond. Sigma bond. Hybrid. This is head-to-head overlap here. What's this guy interacting with? Well, we got another carbon that's the same exact setup. Boom. Boom. Linear. SP, SP. 1 electron from this carbon interacting with 1 electron from the other carbon. So we make a sigma bond to carbon. What's left over on this carbon? Not 1, but 2 p orbitals. There's 1. Well, this other one also has that 1. 1 electron from carbon, 1 electron from the other carbon. This interacts to make what? Side to side. Pi bond. What else is on this carbon that we're looking at? A second p orbital. Okay. Now that one's actually in the plane. All that's in the plane of the board. This other one of the two has got to be orthogonal or perpendicular. The other one here is coming straight out at you like this. And half of it going back. Now that's hard to draw, and that's where it's going to not be so nice here. I'm going to sort of draw it like this. Draw it like this. 1 electron, 1 electron. And it's not good here. These are sort of interacting side to side. These are interacting side to side. Basically what we have here is those 2 p orbitals are coming out like this. And they're interacting side to side to make the second pi bond. There should be drawings in your textbook. I'll show one, not today, next time. Most likely color. They'll use different colors to help sort of give you more of a 3D view. Between the 2 carbons is two pi bonds, sigma and 2 pi. And what is that there? There's your triple bond to carbon and then a sigma bond to H. Okay, when I present something like this, we could sit here and talk for an hour about that drawing. You need to do some reading, more reading, form your questions, and we'll go from there. Hybrid set your geometry though. HC, it's all linear. This is what, H? Okay. Triple bond. Linear. What's the linear, but it's a bond angle of what? The HCC bond angle is what? It is
180.
It is an 8. I mean, 180, right? I mean, that's linear. It's like from 12 o'clock to 6 o'clock. It's actually linear. Okay, bond lengths. Let's see if we can apply this back at the handout again. This is a summary. It comes from a different textbook other than Methane. Questions about any of this? Okay, in this example, both carbons are the same. So when we say sp3, they're both sp3, right? Bond angles, all this, we said that. Bond lengths and strengths. Okay, we don't need to know exact numbers, although it would be good to know, I mean, what type of units, what's the approximate length of a carbon-carbon sigma bond? Okay, 1.5 angstroms, yeah. 1 to 1.5 angstroms, as opposed to like 10 centimeters. Okay, some. But the trend, length of the carbon-carbon bond, the atomic distance. Longer, shorter, even shorter. Why is it longer here?
P orbital.
Well, what orbitals are being used to make the carbon-carbon bond? sp3. What orbitals are being used to make this? Now the sigma bond is what rules. Pi bond doesn't really affect any of this. The sigma bond is made by what? sp2, sp2. That's sp3, sp3. Well, which is the longer orbital? sp3 or sp2? Longer orbital. Two longer orbitals are going to make longer bond. Two shorter orbitals make a shorter bond. So that hopefully makes sense. And then down here, the hybrids are what? sp, sp. This sigma bond, which rules the outcome, if the orbitals are shorter, then the nuclei have to come closer together to bond. If the orbitals are longer, then they can bond without coming so close together. So hopefully this trend makes sense because you're using shorter hybrids to make the carbon-carbon bond. What about strength? Now, kcal or kilojoules. Usually kcal is what I would probably quote. Now, unfortunately, it's a little misleading here. These numbers are for the entire bonding between the two carbons. So they're including the pi bond here as well. Now, it makes sense that a double bond is stronger and a triple bond is even stronger. But is a double bond twice as strong as a single?
No.
No, it's not. Because a double bond is not two sigmas. It's what?
Segment of pi.
Segment of pi. And the pi bond is weaker because that side-to-side overlap is not as good.
Direct term.
Even though you think, well, it's more side. Yeah, but they're kind of far apart. And then this is not 3 sigmas, is it? 3 would be 270? No, it's not. It's a sigma and 2 pi's. Okay?
But it's even less than so is the second pi bond even less energy than the first pi bond?
I have to digest that a little bit. It can be a little bit confusing. I'll have to digest what you just said. Let's just talk about the sigma bond, which is, I don't think, really listed here. Which is a stronger sigma bond between these here? Which one has the strongest sigma bond?
SP.
Which one has the strongest sigma bond? Sigma bond is made using your hybrids. So says this one.
Because it's 50%.
What?
50%.
50% S, 50% S. 25% S. Which
Yeah.
one's going to make a stronger sigma bond?
50%. SP.
50%, yes. Why?
Because it's more ratio, bigger ratio.
More S. Why does
Yeah.
more S make it shorter? Yeah.
Higher
shorter works in.
intermolecular forces.
Usually a shorter bond is a stronger bond. What about energy of the orbitals? More S character make it lower energy? Yes, you got P and you got S in terms of energy, right? S and then you P's and then, okay, as long as you're the same shell, right? So where would an sp3 fall? An sp3, sp2, sp, would that be right? You have energy? More S characters, the more it's going to look like S, not only in length and shape, but also in energy. More stable, and a more stable orbital is going to make a stronger bond. Because the electrons are in a more stable location, orbital. The electrons are more stable. So, strength. Please digest this table here. Take a look, see what type of questions you have. Trends, though. More percent S character helps you with the trends of length and strength. There's plenty of hybridization questions like in the workbook, sure in your textbook. Please be looking ahead as always. We'll quickly be moving on to the handout I gave you today, the physical properties handout. If anybody has any questions about lab, come down right now. Have a good day, guys.